Hello students, I am Dr. Navneet Kaur from Department of Computer Science and Engineering, SIRT College. Today I'll be taking lecture of subject Digital Systems. The topic which I'll discuss in this lecture is BPSK and BFSK system. Now first we will see what is digital modulation, then we will see BPSK and BFSK system in details. Now, digital modulation. The baseband signal, which is also called message signal, it is having a large power at low frequency. So this signal can be transmitted over a pair of wires or coaxial cables. But it is not possible to transmit the message signal or baseband signal over radio links or satellites or over a larger distance, because in that case, larger antennas would be required to be used. Hence, the spectrum of the message signal has to be shifted to higher frequencies so that the requirement of larger antenna would be avoided and there will be less losses in the channel. This is achieved by using the baseband digital signal to modulate a sinusoidal carrier. This method is called digital passband communication or digital carrier modulation. Now, first, we will see the first type of the digital modulation system, which is known as binary phase shift keying. It is also called BPSK in short. BPSK is a form of digital modulation technique in which the phase angle of the analog sinusoidal carrier is varied to represent the input digital data. We'll explain this concept with the help of diagram also. Now first we will see the basic concept of the system. In the system, the amplitude and frequency of the modulated signal remains constant. Now we'll see in this diagram that say we have a digital message signal. Now the first waveform which we can see here is a digital message signal. Digital message signal, that means it is having only two voltage level, either 1 or 0. So here I have arbitrary binary sequence, which is my message signal. So it is either having high level or low level. Now, this message signal is a unipolar message signal. Unipolar message signal means that it is having only one polarity. That means it is either having a positive voltage or zero voltage. That means only one polarity is there, which is positive polarity. Now, I can change my message signal, which is unipolar message signal, to bipolar message signal, which is also called NRZ signal. NRZ signal stands for non-return to zero. That means this signal will not have zero level. Instead, it will have negative level in place of zero level. That means it will be having higher level in the form of +1 level, and it will be having lower level in the form of -1. That means when the message is 1, it will be represented by positive level, and whenever the message is 0, it is represented by negative level. Now, this is the message signal which I want to transmit over a larger distance. Now, in BPSK signal, what happens? I'll take the help of high frequency sinusoidal carrier. Sinusoidal means that we are having a sine wave, which is having higher frequency as compared to this message signal. Now, in this case, we can see a BPSK signal. Now, since the name is binary phase shift keying, that means the frequency of the carrier signal will change according to the binary message signal. Now, here we can see that usually the sinusoidal carrier is in the form of a sinusoidal, which will go in the form of a sine wave. But here we can see whenever there is a change in the message signal from 1 to 0, there is change in the phase of the sinusoidal, which is equal to 180 degree. So instead of going up, this carrier signal is coming again towards the negative direction. That means here we are having a phase shift of 180 degrees. Again, when there is a change of message from 0 to 1, there is again a phase shift of 180 degree. That means instead of message going towards the negative direction, it is bounced back to the positive direction. So again, whenever there is a change in the level, there is a phase shift of 180 degree. Here again, there is a change in the level. There is again a phase shift of 180 degree. That means the carrier shows the phase shift of 180 degree whenever there is a change in the level of the digital message signal. So this process is known as binary phase shift gain. The word binary is used because the message signal is having only two levels. Two means binary. So this message is known as binary phase shift gain. So now we'll again see the definition. Here the phase angle of the sinusoidal carrier is varied to represent the digital data. Here there will be no change in the amplitude. There will be no change in the frequency. Only the phase will change by 180 degrees depending on the message signal, which can be either 1 or 0. Now since I am using bipolar signal, 1 is represented by +1 and 0 is represented by -1. Now, looking back to the equation of the BPSK signal, now since I explained that there is a change in the phase of the carrier signal, let the carrier signal is a cos 2 pi f naught t, where we know 2 pi f naught is what? It is omega naught, which is angular frequency of the cosine signal. Now here the carrier is always in the form of cos signal. Now A is the maximum amplitude of the carrier and 2 pi f naught, which is omega naught, is the angular frequency of the carrier signal. Now here we can find out the power of the carrier signal, which is always given by A square by 2, where A is the maximum amplitude of the carrier signal. Now, from this equation, I can find A is given by root 2p. So, instead of having A here, I can also write root 2p here. So, the equation of the carrier signal will be now root 2p cos 2 pi f naught t. So this will be the equation of the carrier signal. So here we can see the carrier is root 2p cos 2 pi f naught t. Now, according to the definition of the binary phase shift keying, whenever the message is 1, the carrier will be transmitted as it is. That means it will be represented as an original carrier signal, which is root 2p cos 2 pi f naught t. But when the message changes to 0, there will be phase shift of 180 degree. That means amplitude will be root 2p only. Then we will have cos. But here, instead of having 2 pi f naught t, I will have plus pi also, where pi represents 180 degree phase shift. So here we can see the difference between these two equations. Here, the carrier signal is represented by cos 2 pi f naught t. But when the symbol changes to 0, the carrier signal is cos 2 pi f naught t plus pi. That means there is an addition of 180 degree in the phase. Now we know that cos theta plus pi is minus cos theta. So here, instead of having this whole equation, I will have minus cos 2 pi f naught t. So I'll have equation of S2t is minus root 2p cos 2 pi f naught t. So here we can see when the message is 1, the carrier is represented by this equation. And when message is 0, the carrier is represented by this equation, which is negative of the original carrier equation. So, in general form, if I want to represent the equation of the binary phase shift keying signal, I can write it as ST is equal to BT root 2P cos 2 pi F naught T. Now, what is BT? BT is the bipolar signal which I had represented here. We know BT is 1 when message is 1, and when message is 0, BT is minus 1. So here we can see that for 1 it is 1, for 0 it is minus 1. Now if I'll have message 1, then BT will also be 1. So here instead of having BT, I'll have 1. So the equation of the signal will be only root 2p cos 2 pi f naught t, which is same here, which I had explained earlier for message 1. Now, if I'll have message 0, BT will be minus 1. So here I'll have negative sign. So the equation will be minus root 2p cos 2 pi f naught t, which is same, which I had shown earlier for message 0. So this is the general equation of the BPSK signal. Now, for generation of binary phase shift keying signal, in generation, we have a block diagram in which I have input as a digital message signal. Now we know that the digital message signal is in the form of 1 and 0, but I want to change it to 1 and minus 1. So I'll put it into bipolar NRZ encoder, which will change it to BT, where BT will have now two levels, 1 and minus 1, which I have shown in this diagram. This is original message, which is in the form of 1 and 0. I have changed it to BT, which is in the form of 1 and minus 1. And now for changing it, I have used encoder here. Now this BT will be given to balance modulator, whereas the second input to this balance modulator is the carrier signal, which is my original carrier signal with frequency F0. Now this balance modulator will act as a multiplier. So when these two signals will be multiplied, I'll get my BPSK signal where BT and this carrier is root 2p cos 2 pi f naught t. So BT will be multiplied by root 2p cos 2 pi f naught t, which will give me this equation, which is the equation of the BPSK signal. So this is how the BPSK signal is generated using balanced modulator. Now, next we have binary frequency shift keying. Now we have seen that in binary phase shift keying, now we change the phase of the carrier according to the message signal. Now, in BFSK, the frequency of the carrier signal changes according to the message signal. Here, there will be no change in the phase. There will be no change in the amplitude. Only the frequency of the carrier signal will be changed according to the message signal. Now, we know that the original equation of the carrier signal is root 2p cos 2 pi f naught t, where the frequency is 2 pi, where the angular frequency is 2 pi f naught. Now, since there is change in the frequency, we will see that when message is 1, original frequency was 2 pi f naught. But for message 1, the frequency will be added by some amount which I have represented here as by this symbol. Whereas when message is 0, the frequency instead of increased by ohms, it will be reduced by the same amount. So here I will have minus sign in place of plus sign. So for message 1, the modulated signal is cos 2 pi f naught plus ohm t, whereas for message 0, the modulated signal will be cos 2 pi f naught minus ohm t. So here we will see there is change in the frequency by amount ohms. Either it is increased by this amount or it is decreased by this amount depending on the message signal, whether it is 1 or 0, or we can say it is 1 or minus 1. So here I have told you that I'll change first unipolar message signal to bipolar. For 1 it is plus 1, for 0 it is minus 1. So the general equation for the BFSK signal is root 2p cos 2 pi f naught plus ohm, and with ohm I have dtt. When message is 1, this will be plus, so the frequency will be added by ohms. But when message is 0, dt will be minus. So I'll have 2 pi f naught minus ohm t. That means I'll get this equation 2 pi f naught minus t. So this represents the general equation of the BFSK signal. Now here we can see the waveform of the BFSK signal. This is my message signal. This is original carrier signal, which is having frequency f naught. Now here I can see the BFSK signal. When message is 1, the frequency is high. But when message is 0, we can see the frequency reduces because there are less number of seconds, a less number of cycles. So here the frequency is reduced. Now again when message is 1, the frequency of the carrier signal is increased. But when message is 0, the frequency is reduced. So this process is known as BFSK system, and this waveform is known as BFSK modulated signal. Now this is all for today's lecture. Thank you.